So welcome to MCS 471. Welcome to the first lecture of numerical analysis of the fall semester of 2021. So this lecture is being pre-recorded for facilitating the hybrid in-class online way of running the course. So the purpose of this very first lecture is to explain what the course is about. That's the first big item. Then I will explain what is Julia and what does this have to do with the course. And the main part of this lecture will actually be on the fundamentals. One needs to know what algorithms are and what are number systems. So let's get started. So what is this course? What is in it? So numerical analysis is a very classical topic at the interface of mathematics and computer science. It is analysis, it is a part of analysis, but it is actually essentially extremely useful for anybody who wants to do computations on a computer, because computers are still optimized for what we call floating point arithmetic. So here you see the official catalog description and the prerequisites. So the prerequisites are very modest. However, I would like to caution that this is a course for senior undergraduate students and for beginning graduate students. So if you have senior status as an undergraduate, then you are welcome in this course. If you do not, please be advised that some topics and the level of the course might be at a higher level than what you might be used to from a sophomore course or even a junior level course. So third important thing on this slide is that it is a computational course. I will try to explain what I mean by that, but it has a precursor course, and that's the Introduction to Symbolic Computation, MCS 320, and it has a follow-up course, so course 471, which I will teach next spring. So this is already an advertisement for a sequel course. What does MCS 320 do? So the title of 472 seems straightforward. MCS 320 introduces you to the use of mathematical software. So this is a computational course, and it will assume that you can actually already use software. The official prerequisite is a programming course. If you can program, much better for you, but at the very least, so, and actually what's most important, what you need to be able to do is to use software. That is the essence in computational class. All right, so more precisely, so we have the catalog description. What is now the actual content of the course? So in this course, we follow quite closely the first 8 chapters of the textbook of Timothy Sauer on numerical analysis. The second edition is mentioned, other or earlier or later editions are just fine as well. The textbook is not required, but at the same time strongly recommended. If you want a second opinion or another voice, then if you rather read a book rather than sitting through these lectures here, then please look very carefully at the book. It's a good book. So here very closely, very in more greater detail, I have outlined the main topics of the course. The book has more than 8 chapters, and there are actually at least 3 different courses, 3 different styles of numerical analysis that can be taught. We are following the classical calculus-based numerical analysis. So this implies that we will apply methods of calculus. Taylor series will occur many times throughout this course. So it's a calculus-based course, which actually means that we use concepts from calculus. It does not mean that it is a calculus course. The level is again much higher than what you may have encountered in a first year or second year or third year calculus course. I will get into the expectations in a minute. But here you see already there is a midterm exam and there is a review. Actually, there are 2 midterms exam and there is also a final exam. So for the concepts, to check whether you understand the concepts, the exams will be used as the main method of evaluation. So let me now get into the expectations for this course. So what is this course about? So we are studying algorithms for continuous problems. So in a way, the first goal is kind of saying, you know, if you want to solve something, numerical analysis is the way to do it. Well, numerical analysis, as we will make more precise in the second lecture, is the study of algorithms for continuous problems. We will narrow that down. The second goal means that we are interested in accuracy and efficiency. Stability and condition are 2 technical terms which we do not have defined yet, and will not define it in this lecture, but one has to understand when you can obtain highly accurate results and when not. Efficiency is very important. In a way, we will get to that, how to measure efficiency. I will say the third goal is actually numerical software. So this is a computational class, so that's actually the bottom line. You will be given either scripts that will be made available via the course website, or you will be using standard software. Here I list 3 environments. By default, we are using free and open source. So that is what the GNU means, not Unix. The third bullet point is Julia. The middle software environment is there because of MCS 320. NumPy and SciPy are excellent for numerical analysis, but we will actually go into Julia in this course. The transition from Python to Julia should be smooth. All right, I mentioned exams. So on this slide, I have the main points here. So there is a grand total of 700 points. 400 points come from exams. 300 points come from computational work. Exams are time limited. The 300 points are where you have more time. So everything is, of course, time limited. We need to conclude by the end of the semester, but there are 200 points that go to computer projects for which you may work in pairs. Everything else has to be done individually. So there is homework, and homework is, I will post with every lecture homework problems, and I post them in the middle of the slides. In the middle of the lecture, we have an exercise there, and I will dwell on it during these pre-recordings, essentially telling what is expected of you. So in some sense, the solutions are already given to you in words. You have to write it down in your own words, and you have to do on your own the experiments. So I taught the same course in spring, and there is a very strong correlation between doing well in the course and doing well on the homework. So homework is here rather a modest 100 points, and it might seem that you have to do an awful lot of work to earn these 100 points. But that is actually the essence of it. And the fact that there are only 100 points is that you may fail on those assignments. So you can experiment. So you will get feedback on those homework problems. If you miss a homework problem, it will not cost you much. Miss a problem on a midterm exam, it will cost you more. Miss more on the final exam, it will even cost more. So the bottom line on this slide is that there is a more detailed syllabus and there is a course website. So this is where all information more detailed will be posted. So for this pre-recording, I will default this. All right, that is about it. At this point, I'm 10 minutes in. I will start pausing for questions. This is a hybrid course. In class, you can ask questions, but you can also ask questions during office hours, which will be arranged online. All right, the second important point in this lecture is about Julia. So how do you get to Julia? Well, Julia is a free and open source software. It's quite easy to install. So I have the 4 points that need to be executed, and follow the instructions is actually the main instruction. We will be using Julia 1.6.2. I do not think that there is much difference between 1.5, but still, if you have an older version of Julia, it might be good to update. Most likely during the semester, there might be an upgrade. I do not expect them to jump immediately to 2. So any upgrades during the semester will most likely be minor. So but 1.6 is actually the stable version. So the first way to run Julia is either as a calculator in an interactive terminal window, or a PowerShell window. So that's the first way. Also at the command prompt, you can type Julia and then the name of your Julia program. So Julia is a programming language, which if you have taken a course in data structures using C++, means that you have to compile, you have to link the object files before you can do some running. And most likely you need to, as soon as the program gets larger, you need to link with other libraries as well. Julia takes care of this. Julia is just as easy to use as a scripting language. So that's the first selling point of Julia here. Just as easy as Python, but it is, unlike Python, specifically designed for scientific computing. So that's one of the reasons why we are using Julia. All right, there is a second shoe that is about to drop here. So we have the programming language, and we also have the notebook environment. So if you took MCS 320, then you must already be familiar with the Jupyter notebook. The first two letters are Julia, the second two are for Python. So proper pronouncement is not like in the name of the planet, but is Jupyter. So Jupyter is just as essential as Julia for several reasons. So first of all, there is already an exercise popping up, and it's exercise 0. It's the most important exercise of the whole week, and it's exercise 0 in the sense that it won't be collected. And also what I'm getting now is that it's a web-based interface. If actually you miss it, no problem. There are web-based servers, there are web servers that will actually run Jupyter notebooks for you. So I'm assuming in this course, perhaps I should have said this right at the start, that everybody has a computer, or has access to a computer. We used to have the scientific calculator for this course. I taught this course many years ago, and then the scientific calculator was the standard tool. Now actually we have the World Wide Web at our disposal. So we are in the area of cloud-based computing. So if you are confused with installing software, and installing software is the most frustrating thing that can happen because it happens at the time when you don't know the software right well. I do understand this. So if this does not work, don't panic. So there is the cloud that will help you. And we will get to that many times this course. Now again, if you have a computer on your own, you don't need to compile from scratch. There are installers that will get you to the notebook. All right, so this is a computational course. So having the computations running, so in a programming course, it's extremely important that you get some output that comes out of your input. Here, the output is only the beginning. And what is important is that with the Jupyter notebook, you can document your computations. So you can describe what you see. So in this course, the Jupyter notebook is essential for submitting your work. So this is a hybrid in-class online course. So everything can be done online, exams as well. Don't worry, I have many of the questions and I can make many versions of the exam. So you will need to submit your answers in a notebook. Where do you run it? Do you run it on your own computer? Do you run it on the cloud? That can be anything, but it is important that you can use the Jupyter notebook. All right, so this was the second part. So 20 minutes in this lecture, and I have essentially told the essence of the course. So now I will continue in the next half hour explaining the fundamentals. So the fundamentals, or two of the fundamentals. So the textbook also goes into calculus. So there are three fundamentals what the textbook outlines: algorithms, number systems, and calculus. Now I'm assuming already that you have taken many calculus courses, so I will not drag you into calculus, but we will see calculus all the time during this course. Instead, I will say about the fundamentals, about algorithms, and also then about the numbers. So here is our algorithm, described in three ways. So the title of the algorithm will be evaluating a polynomial. What is a polynomial? So a polynomial is a finite collection of monomials with a coefficient. So a term is actually a product of a coefficient and a variable. So this is what a polynomial is in words. It's important that you know, first of all, what is the input data for any algorithm, for any program. And this is described first informally. So you have an idea, it could be in your head, but then it's described formally as well. So the formal transition, so here is where the mathematical formalism helps us so much. We have superscripts and subscripts. Subscripts for the coefficients, superscripts for the powers. The x is a variable, which is just a symbolic name. So in a symbolic computing course, we actually will store the symbol as well. In a numerical course, we actually only store the coefficient vector, the array. I'm already here launching ahead. I'm still using the sequence of coefficients. So if you took data structures are essential to the algorithms. In this course, we can mainly stick to the data structures that are given to us from mathematics. Third important point is actually the dimensions of any problem. And here for the polynomial, this is the degree. What is the degree of the polynomial? What is the size of the input? So we are interested in efficiency in this course, and we will most likely always express the cost and often the complexity in the dimension, in the size of the input. Here we define the degree as the highest term for which the coefficients is different from 0. So the formal description really settles in very clear terms what we mean by a given polynomial of degree d. And now we can state the problem. What is the problem? We have a polynomial given. We also have a value for x. And then what we want is the value of the polynomial at that value for x. Here it is again stated in words, but this is important. So a lot of confusion with algorithms happens simply because people do not understand what is the precise input, what is the precise output. Read the problem specifications. So this is a computational class. You must be able to parse a problem statement. Because the problem statements will show up in the input and output of a function or a program. Now, how do we design an algorithm? Well, all our algorithms solve mathematical problems, so we can write it shorter. So that's the neat thing about mathematics. Often we have very shorthand notation. So what we actually are doing is that we are summing evaluated terms. And here we have the big sigma there. The big sigma looks a bit scary, but it has an input, which is the beginning of the sequence that you sum, and it has an other term, which is the d, which is the other parameter, where you stop summing. So actually you could see the big sigma from mathematics as a function that takes in two parameters, where you begin, where you end, and then the sequence that you sum. So in a way, framework languages make programming very easy because there is already a built-in sum. We will see in Julia there's also a sum there. But at the other side, it's often a little bit harder because the most basic algorithms have already been provided by you. Okay. So in a computational course, we first look, is there already something available in the language, in the system that we are using? And indeed there is the sum. So a good practice in mathematical program solving, the problem of polynomial evaluation is very much like taking a sum. And this sounds quite basic, but making a sum accurately and efficiently is not trivial. So as things starting to scale, how you do it is not trivial as well. So that's also the reason why framework languages have so much functionality. One can count on the most efficient implementation of the basics. All right, I did actually skip over it, but there was another argument that you must have noticed is that, perhaps I will go back, is that I actually wrote the polynomial differently. Instead of going from high degree to low degree, as we normally would do, I write it from low degree to high degree. And that's why so that's a convention that's actually quite convenient for the arrays. All right, so the arrays actually go from the small indices to the higher indices. And here is a little bit of critique on Julia. All arrays must start at 1, not at 0. So in Python and in C and C++, we started 0, which is in the context of polynomials actually better. But one has chosen that all arrays in Julia start at 1. Again, there is an intermediate step that you will need to do mathematically. You will need to adjust the input parameters, where you start your sequence, where you end your sequence, in the mathematical formula. Okay, that means that the power of your value that you provide for x has to be decremented by 1. And then we have a one-liner. So you can see that the translation of the mathematical formula translates into one line. For loops and lists go very well in Python. Instead of lists in Julia, arrays are the data structure by choice. What is the difference between a list and an array? Well, in an array, all elements are of the same type. In a list, the types can be whatever. So one item can have one type and the next item can have another type. Why are arrays better for scientific computing? Well, this allows to optimize the data storage. So we care in numerical analysis about efficiency. So that is why arrays are the more preferred data structure in Julia. Lists are for general purpose programming. All right, so we have thus in one line our algorithm. All right, but it doesn't stop there. So this is not a programming course. So it is a computational course. We are interested in, are we now as efficient as we can be? Well, now look again at the formula. So you can look at the mathematics. I actually gave the earlier original mathematical formula, but you can also look at the code, and you can see with Julia, there is actually no more intermediate pseudocode. All right, so there was a brief hiccup at my internet at home, so I should be restored now. So the formula and the code will guide us through the cost analysis. So we do a number of additions, so as many additions as agree. Now we do one more multiplication as with the coefficients, and then we have the calling of the power function. So with the multiplications, you could say, but wait, there is C naught, and I actually don't multiply. Well, in the algorithm, you do C naught times 1. So we actually have one more multiplication there. And the way it is formulated, so I'm actually looking exactly at the first line on this slide. So we actually do have a call to the power function. So the formula is already here. So this is now our very first exercise. And actually, I have almost given entirely the exercise already, except for the power function. So you can add up the d plus 1, and the d plus 1 calls to the power function. But you have to do a little bit more work in how do you compute x to the power I. Now, you can do this with a binary divide and conquer method if you have remembered one of the applications of recursion, but you can also do it straightforward. So exercises do not have a unique answer. So there is a unique formula, of course, but it depends what reasoning that you have used. So I'm assuming that you also actually took Math 215, Introduction to Advanced Mathematics, is that you can actually go through a mathematical reasoning. All right, functions. One can define functions as a one-liner, but you can also define functions the long way. And why do we do this now? Well, this was not the most efficient way to evaluate a polynomial. And I can already say how it is. It will be quadratic in the degree. And quadratic algorithms are kind of nice, but it means that if you double the length of your polynomial, the time will be multiplied by 4. And we can do better, much better. We can have a linear time algorithm, linear in the degree. And here is where we are getting to. And this is how we compute the powers. So this is another way. I should have pointed this out earlier again. I forgot it first. But why do you write the coefficients from in the opposite way, starting at the degree that is least, going to the highest degree? Well, this is how you accumulate the powers. If you have to compute x to the power 5, well, it goes a lot faster if you have already computed x to the power 4. So what this function does, it accumulates the powers of your argument, the value for x. All right. So there is some syntax here. So coming from Python, I always, if I do some Python programming, I forget the end. So documentation strings are written before the function. Before you write the function, think about the specification. Think about the documentation before you write the code. Very important. Python is moving towards adding type information. Julia has realized that this was actually a very good thing. You can leave off the types, fine, but you can actually add the types. And this also helps the compiler generating efficient code. It also means that you can often write more corrector code. All right. Now I mentioned Math 215. If you know recursion, you know proofs by induction. There's no escape to it. So if you're a mathematician, you say you prove by induction, very powerful reasoning technique. If you are a computer scientist, you solve problems by divide and conquer by recursion. So this is a course in mathematical computer science. We know both, and this exercise is actually a proof exercise. This is not a proof course, and in some sense this exercise is kind of asking among the fundamentals, do you actually know how to write a proof by induction? Now I will say that the base case is already given here. So if you give a proof by induction, you first give the base case, and it is already here. So half of the exercise is already solved, but you have to write in your own words. So what you do with a proof by induction, you actually state what you want to prove, and then you prove the base case. You say it's true for degree 2, degree 3 to degree 4. One of these is fine, and then you make the induction step. So you say actually what happens when you do from degree D to degree D plus 1. And now I get to the computer science part, to the divide and conquer. So you actually see that the nesting, so this is the symbolic way of doing this, is that if you go from a quadratic to a cubic, you multiply everything by x, and you add the next coefficient to it. In the correct way, starting at the highest coefficients. Stars and count number of pluses, you have as many stars, as many multiplications as you have pluses, as you have additions. And that's actually the main statement. The multiplications and the addition. And this is exact. In the algorithms course, you will know the big O. In this course, the distinction with the theoretical computer science course and an actual computational course is that we care about not only what is in the O, what is the constant, but we actually also care what is the actual number of operations that we do. All right, I'm almost running out of time with the time that I had budgeted for the fundamentals with the algorithms. Here is the proper term. So we kind of invented Horner's method with nesting. Here is the algorithm defined in proper Julia code. And you can run this in a, so this will be posted at the course website, or is posted at the course website, depending on when you view this. You can run this at the terminal the classical way before graphical user interfaces. And I will not drag you through this main script here. It takes a little bit of getting used to, but it's always the same moves that we make. The alternative is using the Jupyter notebook. The Jupyter notebook actually tells the different story of this lecture. I have chosen to use the conventional way of presenting the lectures via PDF files that I post. The alternative, and this is how you could also work yourself through this course, is to make a notebook for every lecture. So taking notes in the 21st century, and we are already well into the 21st century, taking notes is often done by electronic means. So using a Jupyter notebook to typeset your documentations, to document your documentations, is actually very good. Notebooks are also programs. I copy the screenshot. Again, this is available or will be available whatever time it is that you're looking at this. The most important thing is that writing a good notebook is writing a good program. So you can execute a notebook just as a program. So this is actually the bottom line, which is displayed here. You can actually run your Jupyter notebook as a program. It's programming, but then in a computational way. All right, I have 10 minutes left for the second fundamental, and this is the binary number system. The binary number system is well familiar to you from an introductory course in computer science. So when we write a number, we don't write the base. So reading a number is actually computing a polynomial at a specific value at the base. So here you see how evaluating polynomials and computing the value of numbers is actually quite related. We're not limited to integer numbers, so we can also work with fractions, and then actually we do have powers of 1/2. And the position determines the power. So here you see it is important to know the convention. So if you look at the dot that separates the fraction from the integer part, the dot is actually the center of the number, and the powers, either of 2 or 1/2, start to increase from that dot. So the example makes it clear how the powers are working. So you go from the dot to the left with increasing powers of 2, and you move to the right from the dot with increasing powers of 1/2. So this is an application of evaluating polynomials. So we now have polynomials that are bits, right? So there is a Julia script that I wrote. Here is the output. If you run this at the command prompt, as I still tend to be doing because I got my education in another century. Then there is the translation from any number into a binary string. So this is also a classic in an introductory programming course. And here I'm trying to indicate also the lists. It's actually an array of anything, but you push to the back of the list, the bits. This is the classical algorithm. So in a way, we are again seeing another algorithms design of the fundamentals. This is the binary expansion of a number in the binary. So the specific algorithm is not so much important. So this is part of the fundamentals. What is important is that there is a finite expansion, and also the base actually matters. So I have 5 more minutes actually to explain this for fractions. So if we can evaluate a binary number into a decimal number, so we had 17 out of 64, then we can do the same thing again if we have a fraction written in our conventional format into binary. So here is the algorithm. And actually, instead of dividing by 2, actually you look for the powers of 1/2. And here is the algorithm as you see it. Actually, this is not the punchline. Here comes the punchline. So if you do this for 110, so it may be a surprise to us with our 10 fingers. So 1/10 and 0.1 are actually very much the same number. So when we see 1/10, we can replace it easily with 0.1 in point format, Or if we see 0.1, we can replace it by 1 over 10. Now, not so in binary. So in binary, the sequence goes on forever. And this is a surprise bit at first, that 1 over 10 is not equal to something with a finite expansion. But you, of course, you have seen this before. Think about 1 over 3, which is 0.33333. So if you had 3 fingers, it would not have been that difficult. But in binary, know that you have an error there. So this makes the segue to what is numerical analysis here. You have to deal with representation errors. All right, I get to the next to last slide. So using the Jupyter notebook, the sooner you learn it, so if you have not already practiced it extensively in MCS 320, then a very good exercise here is to make a Jupyter notebook of the calculations with the binary number system. Again, here, this is a completely open-ended problem. There is not a unique answer. So this is how we see very clearly how plagiarism occurs or not. If there is no right answer, there is no unique answer. So be careful here. This is a warning I want to throw in. Important thing in your answer, again, I'm going to say the answer here, explain all the computations. That the numbers are correct, of course, they should be correct, because you will be copying and pasting the code that is in the binary num.al. You will be copying that number into execution cells. It is important that you can tell it in your own words. You can borrow my words or my explanations if something is not clear from the recordings. And that's the first important thing about this exercise. Second part, the punchline. So in binary number systems, 1 over 10 is not equal to 0.1. All right, so I'm at the end of this. So where do you learn Julia? Well, there are plenty of Julia tutorials available. So how do you learn any language? Well, try to speak it. Try to say something that you know in your own language and say it in other language. Think about your favorite Python script and write it in Julia. There is plenty of documentation available. If you are a graduate student, then the SIME review paper might be good. So also if you are a computer scientist, knowing what is so cool about Julia and modern computing in general, that may be worth reading. All right, I finish off this recording. It will be posted, made available to you.